Ramanujan for G is now available on the Google Play Store. Try it out for free.
So good morning, students. In our previous lectures, we have studied about the dependence of reaction rate on the concentration of reactants. And so there we studied about some very basic concepts in the order of reaction, the molecularity, and we also actually look at the rate law. And rate law in which we studied the differential rate law as well as integrated rate law. And the integrated rate law we have seen for different order reactions, particularly zeroth order and first order reaction, second order reaction as well. We have seen certain equations and the half life and other important concepts we have seen. And now we know that the rate of a reaction also depends on some other factors, and that are temperature, presence of catalyst, surface area, and so on. And we'll look into all these factors one by one into details. And so let's first look into the effect of temperature on rate of a reaction. And what has been seen that most of the reactions, chemical reactions, are accelerated by increasing temperature. So rate of reactions are usually accelerated by the increase in temperature. And if you remember the rate law we know rate is equal to the differential rate law. And the rate is equal to K, which is called the rate constant, into concentration raised to the power certain value, raised to the power certain value, which is called the order of the reaction. So concentration raised to the power order of the reaction. This is what the rate dependence of the rate on the concentration that we see. And what we see, the rate of the reaction depends on what other factor other than concentration? It is the rate constant. So if the effect of temperature and some other factors other than concentration, if we see, there must be their effect on the rate constant, value of the rate constant. So we'll particularly see how the rate value of the rate constant depends on the temperature, the value of temperature, as well as the and how it gets affected if one uses the catalyst. Because in the rate law equations, if you remember, again I am repeating, we have seen the rate depends on the rate constant as well as concentration raised to the power order of that reactant. And so the concentration to the of a reactant to the power order is what it is actually concentration dependent terms only. So rate also depends on the rate constant, and if the rate constant for a particular reaction is higher, the reaction rate will be higher, and rate constant is lower, means the reaction rate will be lower. And suppose certain factors if increases or decreases the value of rate constant, it means that factor will also affect the rate of the reaction. So we see in the rate effect of temperature and the catalyst, we see usually these factors affect the value of rate constant, increases the value of rate constant, and that is why the reaction rate of the reaction increases. And so the most of the reaction, as we see, the reaction rate increases with increase in temperature. It means from the rate law one can easily understand that the means that temperature must be increasing the value of rate constant, because again this value, this equation we know. I'll show you the equation. So any equation you can see here. Rate is equal to rate constant into concentration. These two reactants are there, NO and O2, raised to the power certain value. This concentration, these are concentration dependent. Concentration of oxygen, they depend on the concentration of oxygen raised to the power 1, and it also depends on concentration of NO raised to the power 2. So these are concentration dependent terms. What is the other term? That is K, which is called, we call rate constant. So if rate constant gets affected by certain factors, then also the rate of reaction will change, and that is what we are going to study in the effect of temperature and catalyst. And so for if you look at the certain examples in decomposition of N2O5 dinitrogen pentaoxide, the time taken for half-life of original amount of material to decompose is 12 minutes at 15 degrees centigrade. So to decompose whatever the fixed amount of N2O5 you take, and to decompose half of it, what we require 12 minutes at 50 degrees centigrade. The same amount will decompose if you start the reaction with the same amount of N2O5, so half-life In that case also, we see that half-life is 5 hours at 25 degrees centigrade. So see, half-life was only 12 minutes at 50 degrees centigrade. Now it became 5 hours at 25 degrees centigrade, and it becomes 10 days at 0 degrees centigrade. So as you increase the temperature from 0 degrees centigrade to 25 degrees centigrade, you see that the half-life time required for the completion of half of the reaction, it decreases significantly. From 0 degrees centigrade, it was 10 days at 25 degrees centigrade. It became 5 hours only. In 50 degrees centigrade, it became only 12 minutes. So on increasing the temperature, what we are observing, what we are seeing, the reaction rate is increasing. And this reaction rate is increasing, it means that rate constant must be increasing. So a mixture of potassium permanganate, if you look at another example, and oxalic acid gets decolorized faster at higher temperature than that at a lower temperature. So a potassium permanganate, we know it has a pink violet color. When you mix oxalic acid to it, it gets reduced. Potassium permanganate will get reduced, so its color, pink color, will be decolorized. And so this reaction becomes faster, decolorization becomes faster at higher temperature, and it means the reaction rate is higher at higher temperature, even between for the reaction between KMnO4 and oxalic acid, means the potassium permanganate and oxalic acid. It has been usually found that for most of chemical reactions with rise in temperature by 10 degree, the reaction rate is nearly doubled. So usually it has been seen reaction rate almost becomes doubled with an increase in 10 degree centigrade temperature. And this we call the value, this ratio we call T plus 10 divided by K as reaction coefficient or Q10 value. So the temperature dependence of rate of a reaction is explained by Arrhenius equation, and the Arrhenius equation actually tells us how the rate constant, value of rate constant depends on temperature. And as we know, the temperature affects the rate constant, so temperature will affect the rate of the reaction because rate of the reaction depends on the rate constant. From the rate law, we have this information. So the rate constant is the value of this rate constant is K, then K is equal to A to e to the power minus EA by RT, where K we know is the rate constant, EA is activation energy, this is one term that we know. We keep the value of activation energy usually unit in joule per mole, and R we know it's a universal gas constant and its value is at 0.314 joule per mole per Kelvin, and the value of this unit of this value also depends on the unit. You change the unit, this value will change. So it will come 1.97 if this value is in calorie, 1.97 around, and the activation energy. So, but in that case, what you have to do, you have to also take this value in calorie. If you take this value in calorie per mole per Kelvin, so this value should also be in calorie per mole. So whatever the unit you take for EA, you should also take value of R in the same unit. And the T is the temperature. We know usually we represent temperature with the symbol T, and this value e to the power minus A by RT. So exponential minus A by RT because it represents the fraction of molecules that have kinetic energy greater than EA. The EA is what the activation energy. What is the activation energy? We will see a bit details in the following slides. So just you should remember, this is the activation energy. Activation energy, this is the energy which is required for a reaction to happen. And this energy, if the reactant molecules by itself because of the collision gain that energy, so it will actually cross that. It will be converted into the product. And if the reactant molecules do not have that much energy, so they will not be converted into the product. They will remain with the reactant form. And A, this capital A. Capital A is what? It's called pre-exponential factor. So this is before the exponential. So pre-exponential factor. We also call it frequency factor or Arrhenius factor. So other names of A is pre-exponential factor or Arrhenius factor. And this is a pre-exponential factor. So its other names are Arrhenius factor or frequency factor. And this is constant for a particular reaction. So this pre-exponential factor or frequency factor or Arrhenius factor is constant for a particular reaction. And this value E, the activation energy, or energy of activation, this is also constant for a particular reaction. So EA does not depend on the temperature, it is constant for a particular reaction. So this equation was first proposed by Dutch chemist J.H. van 't Hoff, but it was the Swedish chemist Arrhenius who provided its physical justification and interpretation, and that is why it is known as Arrhenius equation. And so if you look at the example of hydrogen, dihydrogen reacts with diiodine to get 2HI. So H2 gaseous plus I2 gaseous. We know usually standard form of iodine is solid, but I2 in the gaseous form should take the H2HI. Two molecules of HI gas is produced. So in this reaction, what we usually see, this is the H bond, this is hydrogen molecule, and I is their single bond. When these two reactions they react, they first of all they form an intermediate complex, and that intermediate complex, to form this intermediate complex, certain energy is required. And so this intermediate complex, the difference in energy between this and this energy of this we call the activation energy. So energy of intermediate complex minus energy of the reactant is called activation energy usually. And so this is called this intermediate we call activation complex, and energy, the difference in energy is called the activation energy. So they had certain energy, these molecules had certain energy, and to form the activated complex they require certain energy, and that energy is called activation energy. Means to activate these molecules to perform a chemical reaction, then required energy called activation energy. And now once this is a very unstable state, and this is what Arrhenius said, and this in this unstable state, this will convert into the product immediately for a fraction of second, for a very a smaller time, short period of time. This will be formed, and then it will be converted into the product. This is what he suggested. So according to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate, and this molecule of this and this they collide to form an intermediate, and this intermediate we call activated complex, and one can represent this as C. This intermediate exists for a very short time, and that is, it means what? It breaks up to form two molecules of hydrogen ion. So it breaks up. So what happens? These bonds are broken. Here two bonds are being forming here. These bonds are weakening. These two bonds are weakening, and the two new weakened bonds are being formed in the intermediate complex that we call activated complex. This is what Arrhenius proposed. And later on, these bonds, two bonds get broken completely. This HH bond and IA bond, and two HI bonds get formed, and so we see formation of two HI molecules. And the energy required to form this intermediate is known as activation energy. So energy required to form this intermediate or the activated complex is activation energy. These molecules had already certain energy, and from there some more energy, some extra energy is required, and that required energy we call as activation energy. So if you draw an energy profile diagram for a reaction of this reaction, of that we also call potential energy versus reaction coordinate plot. The potential energy versus reaction coordinate plot, or we also call energy profile of that reaction. If you look at the energy profile of the potential energy profile of that reaction, what we see, the H2 plus I2, they had certain energy. Suppose they are at this level, their energy at this level, the potential energy. And the activated complex, that C that is formed here, the energy of that activated complex is somewhere here on this plot. So what we see, that difference, this energy between this energy, this is what we call the difference from here to here, the activation energy. This H2 energy of H2 plus I2 was already at this point. And the energy from 0 to this we call the threshold energy. From this energy level to this level we call threshold energy, and this energy level to this level we call the activation energy. And this potential energy is plotted against the reaction coordinate. Reaction coordinate means reaction progress. And how the reaction progress? Reaction progress along a certain direction, certain coordinates. And what is that direction? So two H2 molecules that we have, one H2 molecule and one I2 molecule that we are taking, and the new bonds will slowly be formed between these two, and these two bonds will slowly be broken. So that is what is actually it represents the reaction. Coordinate is the progress of reaction. And suppose there are other extra atoms and molecules. These molecules could be larger molecule, like even the CH4 if you look at, plus O2 gives CO2 plus H2. So there are even more complicated reactions. There are many even more larger molecules that react they undergo chemical reactions, and only few bonds are broken. Rest of the bonds are unaffected. So the reaction coordinate means the direction along which the reaction is actually proceeding, means along which a particular chemical bond is being broken or formed. Those only represents the reaction coordinate. So reaction coordinate represents the profile of energy change. So profile of energy, whenever the bond is broken in certain direction, then only the energy will change along that direction. If certain bonds, certain chemical bonds in the chemical species are not affected, so then the energy will of that entire molecule will not change because of that, because that chemical during the chemical reaction that bond is still intact with the same energy, same value. So the reaction coordinate represents the profile of energy change when reactants change into the products. So some energy is released when the complex decomposes to form products. So what we know, so once the energy, some energy is required, and after absorbing that energy, these reactants will form the activated complex. And after the activated complex is formed, so this activated complex will be broken into the product, the product species. And then once it is broken into the product species, some energy will be released because it was very tense state, very highly G state, high energy and very unstable state, tense state, so it will broken down, and with that broken some energy will be released, and two molecules you see in this example 2HI is formed. This kind of profile one can actually generate for any kind of reaction. Only these values of activation energy, this and relative this value delta S may change according to the reaction, and the activation energy may also change according to the reaction. But in general, the nature of the profile will be the same. And the final enthalpy of reaction depends upon the nature of reactants and products. And this final enthalpy, whether this enthalpy, the similar energy profile we have seen in the thermodynamics as well. So this kind of whether this reactant will be stable, this reactant is more stable than the product, then what will happen? The product will level will be at this side. So the enthalpy will be positive. That will be the endothermic reaction. And in this case, what we see, this is exothermic reaction. The energy of product is less. You can see here this value at this level less than the energies of some of the energies of the reactant, means the energy is released during the reaction, and so the delta H will be negative. This minus this product minus reactant value. So by this much amount negative value we generate, and that is what we call enthalpy, and this is also called the thermodynamics of the reaction. So thermodynamics of the reaction, it depends upon the nature of the reactant and the product, means what kind of reaction it is happening, whether the exothermic reaction is exothermic or endothermic, based on that, and to what extent it is exothermic and what extent it is endothermic, based on that the value of delta H, this value changes. Note that all the molecules in the reacting species do not have the same kinetic energy. So that there are many molecules supposed in the reactant, and this all the molecules may not have the same kinetic energy, as we know. Even from the when we studied the kinetic theory of gases, we have seen that all the molecules do not have the same kinetic energy. And so, and as we also know that there are many molecules, because molecules are very small, and even suppose if you took a 2 gram of hydrogen molecules, only in 2 gram you will see Avogadro number of molecules. So they are usually they are in very large numbers for any given amount of reactant. Then very large numbers in the molecules are very small, they are indistinguishable and identical. So they are indistinguishable and identical. So it is very difficult to find kinetic energy of individual molecules. So one may not estimate the kinetic energy of individual molecules. So it is very difficult to predict the behavior of any one molecule with precision. So what happens? So the Ludwig Boltzmann and James Clerk Maxwell used statistics to predict the behavior of large number of molecules. So what did they do? They used they did statistics to predict the behavior of large number of molecules. There is no identity. They did not focus on identifying the molecules because it was very difficult. They're very tiny. So what they said, okay, we can predict the large number of molecules. Maybe in one form, these molecules may be changing, their energy might be changing from time to time. So, but their overall behavior of the large number of molecules we may predict, and that is what they did. So they describe the distribution of kinetic energy by plotting the fraction of molecules with a given kinetic energy versus kinetic energy. Fraction of molecules means what? Ne by nt. So what is Ne? Ne is the is what? The number of molecules with energy E. So there, if suppose E is the number of molecules with energy E and Nt is the total number of molecules, the fraction will be represented. The fraction of molecules with energy E will be Ne by Nt. So that is what the Ne by Nt is plotted against the kinetic energy of the molecules, and that is what this kind of distribution they obtained. So the peak of the curve corresponds to the most probable kinetic energy, and anyway we understand that the kinetic peak of this in this peak, so fraction of molecules, on the y-axis is the fraction of molecules, the certain energy, kinetic energy, what we know. So this actually represents the fraction of the molecules with certain energy. So with this energy, this fraction of molecules will be there. It is Ne by Nt. So with this energy, this Ne by Nt, this is the fraction of molecules. So what we know, the highest fraction of molecules will be at the peak. So peak of this represents the highest number of molecules with the energy. So this is what the peak of the curve corresponds to the most probable kinetic, and this also we call the most probable kinetic energy as this. The most probable kinetic energy means the highest number of molecules have that kinetic energy. And this is the probability that the most probable value we obtain. So highest occurrence of certain value, and the highest occurrence of certain value, a statistical value that we call the most probable value. And the most probable kinetic energy will be the kinetic energy which the energy which is uh, acquired by highest number of molecules, and that will be the most probable kinetic energy. Anyway, the highest number of molecules having certain kinetic energy is that at the peak of that is what we get. And if you look into this curve, so if there certain value after certain value, this kinetic energy may reach the value of EA, and that is the activation energy. If the activation energy suppose is here, so then there the reaction will not happen because none of the molecules have the kinetic energy equal to the activation energy. So these molecules will never reach to the activated complex formation. So suppose if the activation energy for a particular reaction is here, so this fraction of molecule with this area, we obtain this fraction of molecules will have the kinetic energy more than activation energy, and these molecules will form the product. So these are and so the again I'll read this from here. So they describe means the Ludwig Boltzmann and James Clerk Maxwell. They describe the distribution of kinetic energy by plotting the fraction of molecules, that is Ne by Nt, with a given kinetic energy E versus kinetic energy. So the kinetic energy on the axis is Ne here represents the number of molecules with energy E, and Nt is the total number of molecules. These things I have already explained. The peak of the curve corresponds to the most probable kinetic energy, and how that we know, the maximum number of molecules have this kinetic energy, and that is why this is the most probable kinetic energy. That is the kinetic energy of the maximum fraction of molecules, and maximum fraction is maximum number. The highest fraction is the maximum. There are decreasing number of molecules with energy higher or lower than this value, and this is what this is the peak. So there are decreasing number of molecules with the kinetic energy value lower and higher than this, and this is what we see, that the molecules with the lower energy, their numbers also decreases, and the molecules with higher energies also their numbers also decreases, other factors also decreases. When the temperature is raised, so what we see, when the temperature is raised, the kinetic energy of the molecules will increase, and it means what? So there will be many molecules with a kinetic energy higher than that, and to have that, what will happen? Generally, what we will see, the kinetic energy of molecules having higher kinetic energy will be more, and so this graph will shift to the right. So the peak will shift to the right, and also the peak will broaden because molecules with even higher this value of kinetic energy, their numbers will be higher. The molecules, that curve will also broaden, and the curve will shift to the right because the molecules with the higher kinetic energy value, their number will increase. And so this is a very common sense thing you might understand very easily. So when the temperature is raised, the maximum of the curve, the maximum moves to the higher energy value, and higher energy value means the higher kinetic energy value. So this maxima at the temperature T plus something, it will be this. So the peak will move to here and it will also gets broadened. Higher kinetic value and the curve and the curve broadens out. The curve also broadens out. And if you see this graph, this one, the first one is the graph at temperature T, a small t, and this is the graph and at temperature T plus 10 degrees centigrade. When we see T plus 10 and means 10 degree higher temperature, we see that this graph, the maxima, it shifts to right, and also this graph becomes broadened out. This was actually more constant, this gets broadened out. So the molecules with higher energy, that we see higher kinetic energy, their numbers increases. And what does it mean? The curve spreads to the right such that there is a greater proportion of molecules with much higher energy when you increase the temperature, and that is what we see in this graph. The area under the curve must be constant since total probability must be 1 at all times. But what we see, although this curve gets broadened out and shifts to right, but a total area under the curve must be 1 because it represents the total probability and which must be equals to 1. And so in this graph, what we see, if suppose this was the activation energy because the kinetic energy was this, so if this was the activation energy for a particular reaction, and so the molecules initially at temperature, this black shaded area. So this was the energy. If you integrate this value, if you means if you take the graph, the area under this graph, the black shaded area. So you see this fraction of molecules will undergo chemical reaction because their energy is higher than the activation energy. At higher temperature, what we see, the number of molecules with energy having more than the activation energy increases, and that the curve gets broadened out. It means this also, and it shifts to right, and that we see here. So this extra shaded area also comes into this, and we see this area, this area to entire this area is almost double. Just by guess one can obtain. So what we see is that we can mark the position of E on Maxwell Boltzmann distribution. This we call Maxwell Boltzmann distribution. The Boltzmann and the Maxwell, we see the Ludwig Boltzmann and James Clerk Maxwell. So they both. Yes, so so the area under the curve must be constant since total probability must be 1 at all times. We can mark the position of E on Boltzmann distribution, and this activation energy value of E we have marked here. For suppose this is the value. So increasing the temperature of the substance increases the fraction of molecules which collide with energies greater than EA. So the fraction of molecules which collide with energies greater than EA increases at higher temperature because nature curve shifts to the right. It is clear from the diagram that the curve at T plus 10, the area in the curve that at T plus 10, the area showing the fraction of molecules having energy equal to or greater than activation energy gets almost double, leading to doubling the rate of reaction. So this area, total area, almost becomes double to the initial black shaded area. This is what one can see from the curve as well. Now let's go back to the Arrhenius equation, and that was the Arrhenius equation was what? K is equal to A, capital A into e to the power minus EA by RT. This is activation energy, this is pre-exponential factor or Arrhenius factor, and K is the rate constant, R is the gas constant, T is the temperature. The factor, this e to the power minus EA by RT corresponds to the fraction of molecules that have kinetic energy greater than EA. So in this Arrhenius equation, the fraction of molecules, as we said, having energy greater than EA is this. So this value will one can obtain as e to the power minus EA by RT. So what will be the fraction of molecules which are having kinetic energy more than this, and that fraction of molecules that we get is what? As e to the power minus E by RT. So if one takes the natural algorithm of this Arrhenius equation, so what we take, this ln k will be equal to ln A in the parenthesis e to the power minus a by rt means ln a plus ln e to the power minus a by rt ln, because this is a natural base, so it minus rt e to the power minus a by rt will become equal to minus a by rt. So actually what we get, taking the natural log on the both sides, it will become ln a plus ln a minus a by rt. So this we get, and the plot one can see this in this value. A is pre-exponential factor, which is constant for a particular reaction. Usually, if the temperature is not varied much, this is what we know. The K is the rate constant. The K is rate constant value, which depends on the temperature that we know that we are going to study here. So one factor that depends on the temperature is R. R is the T, and the value of T, and R is constant, gas constant, universal gas constant. A is the activation energy, which is constant for a particular reaction. So everything is constant. What we see, only the variable factor is temperature. Once you vary the temperature, you see ln K value also changes. So if we put this equation, is actually it resembles the straight line equation. Y is equal to C plus mx, one can write here mx plus c. So here this is c. The intercept, value of intercept, and the variable x is what we see here 1 by t. So one can write here ln k is equal to ln a minus a by r into 1 by t. So 1 by t, if I put on the x-axis along k on the y-axis, so y should get an straight line, and this straight line, the intercept of that straight line should be ln a, so it should give the ln a value, and the slope of that straight line is the mx that we write. So it means that slope should give us the value of minus a by r. The slope will give us the value of minus a by r, and intercept will give us the value of ln a, and this is the graph that we obtain a straight line when we plot ln k versus 1 by t. And these values, with the increasing temperature, one can actually get the value of temperature t, and the value of ln k which one can also obtain. And what we see here, here the temperature, lower temperature value is this. The lower temperature value is because 1 by t we have plotted. So 1 by t means 1 by t value is higher, 1 by t is higher, means t has the lower value. So once you increase the temperature, 1 by t value of 1 by t will decrease, and value of 1 by t will increase, and we are seeing that the corresponding value of ln k is increasing. At this temperature, suppose this temperature I see, this 1 by t value, the value of t is very low, and value of t is very low, the corresponding ln k value is also low, so the value of k rate constant is also low. At suppose at this point, if I come and tell me the value of 1 by t is much lower, value of 1 by t is much lower, means the value of t is much higher, because 1 is constant, 1 divided by t is lower, means t is higher value. So the corresponding value of on the graph that we see here, the ln k value of ln k is this, the value of ln k is this, which is much higher. So the k value of k is increased. So what we see, as we increase the temperature, means if you go on the graph from here in this direction, because the increasing temperature is in this direction and not in this direction, this is the increasing value of 1 by t. So this is the decreasing value of t. So the increasing value of t will be in this direction. So as we see the increasing value of temperature, we see the value of ln k is also increasing, and that it means the value of k, the rate constant, is also increasing exponentially, and there is exponential dependence that we see here. So thus it has been found from the Arrhenius equation that, so the plot of ln k versus 1 by t gives a straight line. This is what we have seen. Thus it has been found from Arrhenius equation that increasing the temperature, also increasing the temperature, what we see that the will result in an increase in the rate of reaction, and this will lead to increase in the rate of reaction. Why? Because the value of ln k increases, and an exponential increase in the rate constant. So rate constant, so the rate of reaction will also increase. Another thing is, if by any other method, if you increase or decrease, change the value of activation energy, keeping the temperature constant, even by other trick, if you change the value of EA. So if you change the value of EA, if the value of EA will decrease, so what you will see, the rate constant will increase. And that the change in value of EA, the activation energy, we do that thing by using a catalyst. So catalyst decreases the value of activation energy. And if the value of activation energy is decreased, increase, so what we see the ln K will increase. So that is also right if the temperature is constant. So we see also the activation energy, the temperature and the decreasing activation energy will also result in increasing the rate of reaction, and this we see when we see how the catalyst affect the rate of reaction. And the slope of this reaction is what we know, A by R, and the intercept will be ln A. This thing we have seen here. One can calculate A by A. So, sorry, E and A. So, in this equation, the Arrhenius equation, E activation energy and pre-exponential factor. These are two things because the temperature, with the temperature one can get the rate constant value one can measure, and the temperature one can also measure. With that, what can we get? The value activation energy may not be measured directly, but one can obtain with that this plot. So what can we do? So one can calculate E and even the value of A using these values. And how will we measure this? So if you suppose at the temperature T1, the rate value of rate constant is K1. So that is the experimentally measured quantity. One can measure K1. And then if suppose at temperature T2, the value of rate constant is K2. So this thing we can write in this equation. Suppose the K1 was the rate constant at temperature T1. So one can write this equation as ln K1 is equal to ln A, as we know the A is a constant, pre-exponential factor is equal to EA minus EA by R T1. T1 is the temperature, EA is the activation energy, and for that reaction we are not using catalyst and any other thing to decrease or the value of activation energy, so it is constant value. So T1, the length K1 is equal to ln A minus EA by R T1, and suppose at the temperature T2 this this rate constant become K2, so one can write ln K2 is equal to ln A minus EA by RT2, and this is what we have written at temperature T2 ln K2 is equal to ln A minus E by RT2, and this we can write since A, the pre-exponential factor or Arrhenius factor or the frequency factor, and we are constant for a given reaction until unless some extra factors are added. And so, and the only changing factor is the temperature. So what we know, the K1 and K2 are the values of rate constants at temperature T1 and T2. This is what I have already said. So subtracting the above two equations, so what can we do? The ln K2 minus ln K1 we can write. So this equation we subtract the first equation, this one from this equation. So what we get, ln K2 minus ln K1. The left hand side things will be subtracted and the right hand side thing will also be subtracted. So ln A is here and ln A is here. So these two things will be cancelled out. And this then on the right hand side will be minus A by RT2 minus A by RT1. So minus minus will become plus. So what we get, A by RT1 on the right hand side, A by RT1 minus EA by RT2. So this we get ln K2 minus ln K1 is equal to EA by RT1 minus EA by RT2. You can use pen and paper and can reach from there to here very easily. That is not difficult because this value get cancelled out, and because this minus the first equation we have done, so the this term will become positive and this will remain be negative. And so ln K2 minus ln K1 we can write ln K2 by K1. Ln K2 by K1 is equal to, now this EA we can take as a common by EA by R. So what we get in the parenthesis, 1 by T1 minus 1 by T2. So this equation you can remember, or what can you do? This is the natural base. So natural base you can convert this natural base into base 10. So we can do this by simply multiply. We can base e, we can change it to base 10, and what we have to do, we have to just multiply by a factor 2.3033, and this will be easily converted. So this is equal to ln K2 by K1 is equal to 2.303 log base 10 K2 by K1, and this right hand side is same, E by R1 by T1 minus 1 by T2. One thing you should remember here is the K2 by K1, whatever the unit you take here and you need to take here, that those units will be cancelled out. So in solving the numerical problems, we only put the numerical values here and not the, because the units will be cancelled out. We will see later on how it will get cancelled out. So anyway, from here this 2.303 will go here, So log K2 by K1 means this is log base 10. K2 by K1 is equal to PA divided upon 2.303 R 1 upon T1 minus 1 upon T2. This equation you should remember, or if you can't remember this, so the next step will be what? So this T1 and T2, this will become T2 minus T1, or further solving this equation. You should remember either this or this. Anyone, if you can remember, you can do. Even if you don't remember, you can. If you know this process, you can derive this equation from the Arrhenius equation. But for that, you need time, and that much time you may not get in the competitive examination. So that is why it is important for you to remember either this or this equation. They are actually basically same. But simply this is more simplified. So let's see this numerical problem. The rate constant of a reaction at 500 Kelvin and 700 Kelvin are 0.02 into per second and 0.07 per second respectively. So what we see in this numerical problem, with increasing temperature, rate constant is increasing. That means rate constant is increasing, the rate of reaction is increasing. What we have to calculate is the value of E and A. So we have to calculate means this a value of activation energy and the pre-exponential factor. And the value of activation energy we can calculate, that we have seen value of activation energy using this at different temperatures. The rate constant values are provided. This value we know already, 8.314. So this numerical value is joule per Kelvin per mole. So and this value only unknown thing will be the EA. So the EA we can easily get. Now once we get the value of EA, we can go back to the Arrhenius equation, that is K is equal to A pre-exponential factor into e to the power minus EA by RT. And there, once we know the value of EA, we can put rate constant at any temperature. We can take the value and the corresponding temperature we can put, and thus we can get the value of the exponential factor A as well. And that is what we are going to follow in this numerical problem, the same process. So what is given at temperature T1 is equal to 500 Kelvin, rate constant K1 is given 0.02 per second here. And at temperature T2 equals to 700 Kelvin, rate constant K2 is 0.07 per second. So this equation will solve to this equation. Log K2 by K1 is equal to VA by 2.303 R into T2 minus T1 by T1 into T2, or you can also follow this equation there. So we'll follow this one. And now we can put the value of log I, as you can see here, 0.07 per second, and divided by the value of K2. And the value of K1 is what? 0.02 per second. This per second will be cancelled out. This was what I was saying. So even if you take later on, if was required, you have to write this thing into log K2 minus log K1 in this form. Even in that case, you have to only put the value of this numerical values and not the units, because the log with unit value has no meaning. But log of any numbers can only be taken, and we see that because the units are cancelled out, so actually we get numbers only there. Even in the log K2 minus log K1, even if you write those values, these values without unit, it will have same effect. So what we get, so the log K2 by K1, value of K2 and K1 we put here, and activation energy A we do not know, we have to find out, divided by 2.303, value of R we know, 8.314 joule per Kelvin per mole, into T2, value of T2 is what? 700 Kelvin minus T1 500 Kelvin divided by 700 Kelvin plus 500 Kelvin. So actually this is T2 into T1 I have written. The same order. Anyway, the result is not going to change, only the order was changed. Because so 500, this is a T1 into T2, 700 Kelvin. So 1 Kelvin take get cancelled out anyway. So EA will be what? EA will be equal to log 0.07, and this 0.07 divided by 0.02 will become 7 by 2. So because this decimal, this is 10 to the power minus 2, 7 into 10 to the power minus 2, this is also 2 into 10 to the power minus 2, 10 to the power minus 2, 10 to the power minus 2 will be cancelled out. So this will become log 7 by 2, and log 7 by 2 means log 7 minus log 2. So this is simplified here. So EA will be equal to log 7 minus log 2 into this value will multiply to this 2.303, this will multiplication into 8.314 joule per Kelvin per mole, and this term will be in the multiplication, so this will be reversed, so 700 into 500, and this 1 Kelvin, and this there is 1 Kelvin above, so one can take 1 Kelvin as a common here, 700 minus 500 one can, right? So this 700 minus 500 will become 200 Kelvin, and 200 Kelvin, so 1 Kelvin and 1 Kelvin, so this will become 700 into 500 Kelvin, 1 Kelvin divided by 200, and so this Kelvin cancels out, you can see here. Anyway, so the EA will be what? The value of log 7 is 0.845098 up to here only. You can also put minus 0.30103 into 2.303 into 8.314 joule per Kelvin per mole, and this into 700. This two zeros and two zeros there, it will cancel out, so it will become 700 into 500 K divided by 2, and this K, you know. Now this value on further solving it becomes equal to 0.54407 into 2.303 into 8 point this. So further simplification, and after overall solving all this, doing all the numerical in this calculations, what we get this value is 18,230.4 joule per mole. So Kelvin and Kelvin we will consider. So what will be the unit? Joule per mole, and this is what we see the unit of activation energy as shown earlier. We usually obtain in joule per mole. So this will be in the joule per mole. So this joule per mole usually one can also write it in the kilojoule per mole when you report the final value. Sometimes it is given. So to do this into kilojoule per mole, so what this value one can write 18.2304 into 10 to the power 3 joule per mole, and 10 to the power 3 one can write as K, the kilo. So that will be equal to 18.23 kilojoule per mole. Now we know the activation energy, value of activation energy we have calculated, and from there one can also calculate the pre-exponential factor using the Arrhenius equation. So what we know, K Arrhenius equation, K is equal to A e to the power minus A by RT. This is Arrhenius equation, and the value of K one can write at a given temperature, any value one can write at a 500 Kelvin, 0.02 value activation value of K, or 700 Kelvin, 0.07. With any values we can obtain the same value. And what I have taken is at the values at the 500 Kelvin. So the 500 Kelvin, the rate constant I have taken 0.02 per second is equal to pre-exponential factor A into e to the power minus activation energy. Activation energy given value minus 18. This minus is because of this. This is 1823 0.4 joule per mole divided by value of R 8.314 joule per Kelvin per mole into 500 Kelvin. And this Kelvin, you see this Kelvin will be cancelled out, this per Kelvin, Kelvin, this per mole, per mole will be cancelled out, numerator and denominator, and this joule will be cancelled out. So we get only a numerical value on the exponential. So this is equal to A e to the power of solving all these values, we get e to the power minus 4.38546. And so this is equal to, this equation is equal to 0.02 per second is equal to A into this value e to the power minus 4.38546 is equal to 0.012457. So A will be equal to 0.02 per second divided by this. So the value of A will be equal to 1.61 per second. So the pre-exponential factor or the frequency factor or the Arrhenius factor one can also obtain with using this method. Now let's see this question. So the first order rate constant for the decomposition of ethyl iodide by the reaction CH2H5i. This is a ethyl iodide, the gaseous, gives C2H4. This is ethene plus HI gaseous. So ethyl iodide it gives HI. So this is the elimination reaction. If you know the organic reaction and if you remember this is elimination reaction. So HI is eliminated from C2H5i. So at 600 Kelvin, what we know, one is given is 1.60 into 10 to the power minus 5 per second is the rate constant. And since the unit is per second, this one can also find out that this reaction is a first order reaction. Because the unit of rate constant is in per second, it means that from the unit of rate constant also one can find out the rate of the, order of the reaction. The reaction per second, it is the first order reaction. And how one can find out similar examples, we have seen some numerical problems previously in the previous lecture. So its energy of activation is 209 kilojoules per mole. So energy of activation is also given, although one can find out this value is very high value of the activation energy. So this reaction will usually not happen at the room temperature. One need to heat this for this elimination reaction to happen. So anyway, this is very high activation energy value. So calculate the rate constant of the reaction at 700 Kelvin. So what we have to calculate is the rate of reaction at 700 Kelvin, and what is given is, sorry, the rate constant we have to calculate at 700 Kelvin, and what is given is the rate constant at 600 Kelvin, and the activation energy is also provided. So the same method we will follow, the method that we use to calculate activation energy. In this case, what is given is the activation energy value of activation energy is given, but what is not given is the value of K2. So let's try to solve this question. So what is given as a temperature T1 equals to 600 Kelvin. The rate constant K1 is this 1.6 into 10 to the power minus 5 per second. Energy of activation E is also given 209 kilojoule per mole. It means 209 into 10 to the power 3 joule per mole. The kilo means 10 to the power 3 that we know. And at temperature T2, 700 Kelvin, rate constant K2 has to be found out, and this is what we are going to do. So we can resort to the same equation that we have used in the previous example. This log K2 by K1 is equal to EA by 2.303 R into T2 minus T1 by T1 into T2. And so to remember the K2, so the T1 will be here and the K1 is below, the T1 is here and the T1 into T2 is here. So one can find out different tricks to remember this equation for a longer time. So we use the same equation, and in this equation one can write this log K2 minus log K1. And log K2, as I said earlier, log K2 minus K1, I am going to put only the numbers and not the units, because even if you put the units, this unit will be cancelled out here itself in this step. And so the only step that will follow forward is the numbers of the rate constant only. So the K2 will be equal to log K2 minus log K1 is equal to EA upon 2.303 R. R from here into 1 upon T1 minus 1 upon T2. Actually, this we got from this only. And we have seen this here. From here, we got this. So actually, one can write this equation as well. Or simply T2 by T1 minus T2. So T2 upon T1 minus T2 minus T1 upon T1 T2. So the T2 will be cancelled out. So 1 by T1 minus 1 upon this T1 in the next step will next. So the thing it will be cancelled out. So T1 minus T1 and T minus T1 by T1 T2. So it will become 1 upon T2. So let me explain it again. So T2, this is T2 upon T1 minus the T1 into T2 minus T1 upon T1 into T2. In the first thing what we have seen, T2 upon T1 into T2. So T2 T2 will be cancelled out, so it will become 1 by T1, and then the next is what it was T1 upon minus T1 upon T1 T2. The T1 T1 so it will become 1 minus T2. So anyway, this is known to us. So we can write log K2 minus, we can put the values log 1.6 into 10 to the power minus 5. The value of K1 is equal to value of activation energy we can put 209 into 10 to the power 3 joule. Oh, again this I should not write kilo here, joule. Joule per mole divided by 2.303 into R value of R 8.314 joule per Kelvin per mole into 1 upon temperature T1 1 upon 600 minus 1 upon Kelvin minus 1 upon 700 Kelvin. The T1 and T2 value of T1 and T2 have been put here and this is equal to what these values if you solve you will get 10915.47 and this joule will be cancelled out, this mole will be cancelled out. And this per Kelvin will be there and this per Kelvin this would be the Kelvin actually and this per Kelvin will become Kelvin. So there is a unit Kelvin as well. So, sorry. So this. And this is what we get actually T2 minus T1 by T1 T2. Simply, one may not need to write this one. So T2 minus T1 is 700 minus 600. 700 minus 600 becomes 100 Kelvin divided by 600 Kelvin into 700 Kelvin. T1 into T2 from directly from this. So this one may not be necessary here. So this factor might be unnecessary. So again, let me write the same thing here. This is 700 Kelvin minus 600 Kelvin divided by 600 into 700. So, hmm. So this value we can write again. So this thing I have actually again written into the same form. Earlier I tried to write one in the form of 1 upon T1 minus 1 upon T2. That is not necessary here. Actually, this one will actually reduce the one number of steps to the calculation. So anyway, that one can do the 700 minus 600 Kelvin. So it will become 100 Kelvin divided by 600 Kelvin into 700 Kelvin. This Kelvin and this Kelvin is square Kelvin Kelvin. So Kelvin will be cancelled out. So log K2 is equal to log 1.6 into 10 to the power minus 5 plus 10915.47 into 1 divided by this 100 and this 0, 2 0, this 0 will be cancelled out. So this into this. And so this is what the log K2 minus this is this. So, so what we say log K2 minus this is equal to this value. So the log K2 will be equal to this value plus log 1.6 into 10 to the power minus 5. So this is what I have written. Log K2 is equal to log 1.6 into 10 to the power minus 5 plus this entire one. And this value is what? This into 2020 will be cancelled out, and the Kelvin square will also be cancelled out. And log 1.6 into 10 to the power minus 5 is equal to minus 4.8. This value one can find out. This is base 10. And on solving this value, one can obtain as 2.6. So what we get? Log K2 is equal to minus 2.2. So the K2 will be equal to 10 to the power minus 2.2, because we take anti-log here to obtain the value of K2. So the K2 will be equal to anti-log of this. The anti-log of this will be equal to 10 to the power minus 2.2, and 10 to the power minus 2.2 means 6.31 into 10 to the power minus 3. And usually, since it is a rate constant, so later on we should put the unit here, and the rate constant, since the rate constant unit is in per second, so we'll write the rate constant unit as per second. And what we have seen here is again one minor error is this would be smaller case letter. So the K2 is equal to 6.31 into 10 to the power minus 3 per second. So what we have seen on increasing the temperature, rate constant in this case has also increased, because the value 1.6 into 10 to the power minus 5 is lower than the value 6.31 into 10 to the power minus 3. So the rate constant, value of rate constant has increased on increasing the temperature by 100 degrees centigrade, and it has changed significantly in the order of 2, and that is why the rate of reaction increases on increasing the temperature. So one term that I have just mentioned briefly earlier is called temperature coefficient and Q10 value. This is also sometimes used. So the chemists commonly use a rule of thumb that an increase of 10 Kelvin in temperature doubles or triples in some cases the rate of the reaction. And this ratio K temperature T plus T divided by KT is called temperature coefficient and is represented as Q10. And this Q10 value that we see, so let's see this question. So what must be the activation energy for this statement? And this statement to be true for a temperature increase from 25 degrees centigrade to 35 degrees centigrade. So at 25 degrees centigrade to 35 degrees centigrade, we do not know what is the activation energy, is what we have to obtain. And what we know, the K35 by K25, this is degree centigrade temperature, is 2. This is the statement. So rate becomes double. So 2 times. So rate becomes double. So K35. So this is a smaller case letter, capital with the capital K. We write equilibrium constant. So small we represent usually rate constant with the smaller case letter. This was the typing error. So K35 by K25 is equal to 2. And the temperatures that we know, the temperature T2 is what? 35 degrees centigrade means the 35 plus 273, that is 308 K. And the T1 was 25 degrees centigrade means that 25 plus 273 means 298 Kelvin. So one can write log K2 by K1. As we saw, the previous equation is equal to EA upon 2.303 R, T2 minus T1 upon T1 into T2. And now the log K35 degree centigrade divided by K25 degree centigrade, this value we know is K35 by K25 2. This is equal to EA upon 2.303 R T2 minus T1 divided by T1 into T2. Now we put the value, this value is log 2, because this value K35 by K25 is 2 is equal to EA activation energy value we do not know, divided upon 2.303 into the value of R. Value of R is 8.314 joule per Kelvin per mole into this value T2 is 308 Kelvin, 308 Kelvin, because we put the temperature value in Kelvin only, so that is why it was converted into the Kelvin from 0 degree, from degree centigrade. So 308 Kelvin minus 298 Kelvin divided by 298 Kelvin into 308 Kelvin. So this is T1 and this is T2. And so the EA will be equal to This value log 2 we know it is 0.301 into 2.303 into 8.314 this value. So 0.301 into this into 298 into 308 and this value this difference is 10. So 298 into 308 divided by 10 will be equal to EA and this value on solving what we get is 52897.78 joule per mole. This is 52.9 kilojoule per mole. So the activation energy will be 52.9 kilojoule per mole. The next question is the specific reaction rate for the reaction increased by a factor. The specific reaction rate for a reaction increases by a factor 4. The reaction rate it is saying it increases by a factor 4. Temperature is changed from 27 degrees centigrade to 47 degrees centigrade. So what we know, this one thing we have to understand here is the reaction rate depends on the rate constant. And so we have seen the rate of reaction directly proportional to the rate of constant. So if the rate constant becomes 2 times, the reaction rate will become 2 times if the concentration is not the factor that changes the reaction. And if the reaction rate constant becomes 4 times because of the increase in the temperature, the rate will become 4 times. So if it is saying that the rate of reaction becomes 4 times, so it means it is given that the rate constant becomes 4 times on increasing the temperature from 27 degrees centigrade to 47 degrees centigrade. This is the information that we need to understand. And so what we see again, just minor typing error. I think anyway this is not editable. So anyway one can just try log 10 K2 by K1. This K should be in the smaller case letters. So K2 by K1 is equal to 2 A upon 2.303 R T2 minus T1 divided by T1 into T2. The same equation we are following in all the numerical problems we have followed. So substituting the value of R, this value of R one can either write in the form of joule per Kelvin per mole, or one can also obtain this value in the calorie per Kelvin per mole. Chemists usually take the value in calorie. This is what I have also explained earlier. Let's just take the value of R in calorie per Kelvin per mole. So the calorie 8.314 divided by 4.1, it will become 1.987. And we know the joule and Kelvin relationship. So the joule and calorie relationship. So 1 calorie is equal to 4.18 joule. So if the value is given in the joule 8.314, you remember you can convert into the calorie by dividing that value 8.31 4 from 4.18. So that is what value we get, 1.98 calorie per Kelvin per mole. This is one. And this is log 4. Log 4 because the rate becomes 4 times, so the rate constant becomes 4 times is equal to EA activation is divided by 2.303. This value we have put into this 320. So this temperature is what? 47 degrees centigrade means 320 Kelvin. And this 27 degrees centigrade means 300 Kelvin. So 320 minus 300 is 300 and 320. This unit will cancel out also because of the many other units. So what we get finally here is EA is equal to, but only thing what will be left over here is the calorie per mole. The unit that we get here is calorie per mole. So 0.6025 this value into 2.303 into 1.987 into 300. So this 300 into 320 by 20, this is equal to 1322.98 calorie per mole. And this calorie per mole we can convert to kilocalorie per mole. So this is what? 13.311 kilocalorie per mole. You can solve this question as well and can obtain this value by your own. So what are the some important points that we have obtained here is, so wherever we have obtained the value of activation energy, if you remember, it was already positive, always positive. So all the values in the numerical problems, the value of activation energy A we have obtained as a positive value. And so if by solving some numerical problem, sometimes if you get the value in negative sign, with the negative sign, and the value of activation energy with the negative sign, it means you have made certain mistakes, also you should cross check it. So the value of activation energy is always positive, you should understand. And why it is positive? Because if you remember this graph, this is the energy that we need to provide. So this is the energy absorbed by the system and the energy you provide to the system. The energy absorbed the system. So energy of the system, the activated complex, will be more than the energy of the reactor. And if the energy of the activated complex is more than the energy of the reactant, it means the value of whatever the value of this EA, this difference will be positive. And so this value of EA should always be positive. You should remember. Then the larger the value of EA, the slower the rate of a reaction at a given temperature. What is this value one can understand? It means if the value of activation energy is larger, means if its activation energy is not here, if suppose it is here. So the very smaller fraction of molecules will be having the energy equals or higher than the activation energy. So the rate of means the very few molecules will convert to the product. It means the rate of reaction is what? It has decreased. That is why the very few molecules has converted to the product. So this thing we should understand, and the same thing we can also understand with this graph. If you increase the activation energy, if the activation energy is increased, it means very few molecules will obtain this value, this larger value of activation energy to get converted into this. So means you need to provide a higher temperature, higher energy from outside to cross this barrier, because this barrier height you are increasing. So activation energy increasing means the barrier you are increasing. And once you increase the barrier, you need to know that the process will become slower. Any process becomes slower if you increase the barrier, and that we know. And the same thing happens for the chemical reactions as well. And the larger the value of activation energy, the steeper the slope of ln k versus 1 by t. And this thing ln k versus 1 by t, this plot. So if the activation energy value is larger, it means this slope will be steeper. So it means this slope, this value will become like this. So if the activation energy is lower, this will slope will be like this. It means that just by looking at different slopes, if the question asks in which of the graph, in which case the activation energy will be highest, the one with the steepest slope, one can say that that will have the highest activation energy. And anyway, so slope will be negative, so the EA will be slope into R. So value of R, we know the slope is more, the activation energy is more. So here, from here also one can obtain activation energy is equal to minus slope into R. Since we get the slope here negative slope, so minus minus will become positive, certain value into R, and that positive value. So what we get, that the slope is more, the value is more, the numerical value is more, the activation energy is more. So this term is also important, and the questions may be framed accordingly. So high activation energy corresponds to a reaction rate that is very sensitive to temperature. So if that activation energy is very high, so that rate of reaction is very sensitive to temperature, means the reaction may be happen only when the temperature is increased. Now let me finish this point topic as well, and this chapter will be over then. So effect of temperature on rate of a reaction, sorry, that we have seen. Now we'll see the effect of catalyst on a rate of reaction. And what is the catalyst? That the catalyst, we know catalyst is a substance that changes the rate of a reaction without being consumed in in the reaction, or without undergoing permanent chemical change. So that catalysts are chemical substances. What we define it, it actually increases the rate of a reaction without being consumed or without being undergoing a permanent chemical change. That these catalysts may take part in the chemical reactions, but after the chemical reactions, they come out from there, and so their chemistry, their structure, everything is intact. So they undergo. Although they take part in the reaction, but after the reaction, the completion of reaction, they are liberated out, and so they only change the rate of the reaction, but they do not undergo any permanent chemical change. That is how the catalyst is defined. So what catalyst does, how the catalyst increases the rate of reactions, and that we know the rate of reaction depends on the two factor, rate constant and the concentration raised to the power order. Concentration raised to the power order of the reaction, those things we have already seen in the concentration dependence of the reaction rate. While here now we mostly focus on the rate dependence on the rate constant. So The catalyst also affects the rate constant. How it affects the rate constant? Arrhenius equation. We know the activation rate constant depends on the activation energy, and so the catalyst decreases the activation energy. So once the catalyst decreases the activation energy from the Arrhenius equation, one can understand that the rate constant will be higher because K is equal to A into e to the power minus EA by RT. So if the value of EA is lower, so the lower value will be in the denominator because e to the power minus EA means A divided by e to the power plus EA by RT. So the EA value of EA is lower, so e to the power EA by RT value will be lower. So A divided by entire value will be higher, the rate constant will be higher. I hope you understand this mathematical thing. So what happens if you just draw a graph between potential energy and the reaction coordinate, the similar graph that we have seen earlier for the temperature. So what we see, the reaction path, this the reaction pathway without catalyst. So this the reactants, and this, if suppose it follows this pathway to get converted into the product. Once you use the catalyst, it follows another pathway, and this pathway has lower activation energy. So this much energy between activated complex and the energy of reactant is called the activation energy. This energy is lower, means this barrier becomes smaller or lower, and when barrier becomes lower, so the here again the common sense thing that if the barrier is lower, then the any process, anything will be faster for anything. So the reaction, this is the reaction path without catalyst. This one and this one is the reaction path with catalyst, and we see the barrier is decreased. However, what we see, the thermodynamics means the stability of the product and reactant doesn't get changed with the involvement of the catalyst. So catalysts do not affect the overall thermodynamics of the reaction. Means the net energy liberated during the chemical transformation. So if a chemical transformation is spontaneous, then and to what extent then the reaction will still be spontaneous with the same extent after applying the catalyst. So catalyst only decreases the barrier, it doesn't affect the stability, relative stability of the product with respect to the reactant. So the energy of activation, this was with catalyst, and this was the energy of activation with catalyst. What we see, the energy of activation decreases. So it is believed that the catalyst provides an alternative pathway or reaction mechanism by reducing the activation energy between reactants and products, and hence lowering the potential energy barrier. So it lowers the potential energy barrier by following an alternative pathway, and so the reaction rate increases. So it is clear from Arrhenius equation that lower the value of activation energy, faster will be the rate of a reaction, and the activation, the Arrhenius equation we know, rate constant K is equal to A e to the power minus EA divided by RT. EA is the activation energy. It means the rate constant K is equal to pre-exponential factor capital A divided by e to the power EA by RT. So if EA is lower, so e to the power EA by RT will be lower, and e to the power EA by RT will be lower. So A divided by EA to the power RT will be higher, so rate constant will be higher. And so if value of EA is more, then the A divided by e to the power EA by RT will be lower, so the rate constant will be lower, the reaction rate will be lower. Now, there are two forms of catalyst that we talk about, the heterogeneous catalyst and the homogeneous catalyst. The heterogeneous catalyst exists in the same phase as the reacting molecules. So the physical state of the catalyst will be same as that of the reacting molecules. And then the homogeneous catalyst, the catalyst is called homogeneous when the physical state will be, sorry, in heterogeneous catalyst, it will be different. Somehow I made mistake in explaining. Heterogeneous catalyst means the catalyst, physical state of catalyst will be different than that of the reacting species. But in homogeneous catalyst, the catalyst, physical state of catalyst will be same as that of the reacting molecules. So the homogeneous catalyst exists in the same phase as the reacting molecules, and the heterogeneous catalyst exists in the different phase as the reacting molecules. The example we take MnO2 catalyzes the following reaction so as to increase its rate considerably. So 2KClO3 in presence of MnO2 gives 2KCl plus CO2. This is the composition of KClO3, potassium chlorate, and this potassium chlorate decomposes to KCl, potassium chloride, and O2. and this MnO2 catalyzes this reaction. The word catalyst should not be, this is the one thing that you should remember, this word catalyst should not be used when the added substance reduces the rate of the reaction. So there and particularly in the biological reaction, sometimes in chemical reactions as well, what we add certain substances we add and it decreases the rate of the reaction. As we see the acceleration or retardation to different terms in physics, similarly, we see these terms. We call the substances which decreases the rate of reaction. Do not call the substances as catalyst or the negative catalyst. We use different terms for such substances and we call such substances as inhibitor. So if the substance decreases the rate of reaction, it is not negative catalyst, but it is an inhibitor, a reaction inhibitor. The action of the catalyst can be explained by intermediate complex theory, and intermediate complex theory is what that we have seen earlier, by that was we have seen for this. So what happens? The catalyst also associates with one of the reactant or some of the reactants, and it forms an intermediate. And this intermediate formation of this intermediate has a lower barrier, and a further reaction, further conversion also has a lower barrier. Also, it changes the pathway, but this pathway has all the barriers lower than the barrier that we have seen in absence of the catalyst. So although the number of steps with the catalyst increases, but the reaction barrier decreases, and that is why rate of reaction increases in the presence of catalyst. So according to this intermediate complex theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. This has a transitory existence and decomposes to yield products and the catalyst, and this intermediate complex then decomposes to yield products and the catalyst. So catalyst is liberated in the last phase of some of the intermediate steps of the reaction. So a small amount of catalyst can catalyze a large amount of reactants, because since this catalyst is after this reaction is liberated out, now it gets freed. So now this free catalyst again catalyze the next reaction, set of reactions, and so a very small amount of catalyst can catalyze a large amount of reactants. So a catalyst does not alter Gibbs energy or delta G of a reaction, as I have said earlier in this graph. As you see, this both the graphs at reactants and products they merge to at the same place. So it doesn't change the delta G value of delta G for reaction Gibbs free energy or the thermodynamics of the reaction. Thus, it catalyzes the spontaneous reaction. So, catalyst catalyzes the spontaneous reaction but does not catalyze non-spontaneous reaction. So, if a reaction is non-spontaneous in certain direction, but that reaction will not be catalyzed because of the presence of catalyst, means it doesn't affect the thermodynamics. So, it doesn't mean that if you use the catalyst, the reactant, why a reaction is a non-spontaneous in particular direction? Because in that particular direction, the free energy of reactant is lesser than the free energy of the product, and that the positive value we get. So in that direction it was known as spontaneous. And the catalyst doesn't affect the stability of the reactant or product, so it doesn't catalyze a non-spontaneous reaction. So catalyst does not change the equilibrium constant of a reaction, and this is also because equilibrium constant depends on the thermodynamics of the reaction. So catalyst doesn't change the equilibrium constant, rather it helps in attaining the equilibrium faster. So since it increases the rate of reaction, so actually it helps attain the equilibrium faster, but it doesn't affect the rate. It doesn't affect the equilibrium constant. So this point we should also remember, catalyst does not affect the equilibrium constant, rather it helps in attaining the equilibrium faster. Why? Because equilibrium depends on the constant, depends on the thermodynamics of the reaction, and that value, if you remember, log uh, this ln k is equal delta G is equal to minus RT ln k. Delta G naught is equal to minus RT ln k. So this delta G naught depends on the equilibrium constant, depend on the thermodynamic delta G naught. So that is the thermodynamics. So that is, it catalyzes. So rather it helps maintaining the faster, so the equilibrium faster. It means it catalyzes the forward as well as backward reaction to the same extent, so that the equilibrium state remains same but is reached earlier. Since the rate of forward reaction and backward reaction rate constant, it increases in the same amount, and so this ratio k forward divided by k backward doesn't get affected, and that k forward by k backward is what the equilibrium constant. So when the both the direction rate constant gets affected by the same extent, so equilibrium constant doesn't get affected. But this reaction with Kf and Kb, means K rate constant in forward and backward direction, both get affected by the same extent. So this ratio is remains same, but the Kf and Kb both increase, so the equilibrium is attained faster. Now this is the final topic of this chapter, the collision theory. Let's cover the collision theory of a chemical reaction. So though the Arrhenius equation is applicable under a wide range of circumstances, collision theory, which was developed by Max Storch and William Lewis in 1916 to 1918, provides a greater insight into the energetics and mechanistic aspects of reaction. So this is just briefly we'll read about the collision theory, not in the details. So the Arrhenius equation is applicable that we know under a wide range of circumstances. The collision theory which was developed this provides a greater insight into energetics and mechanistic aspects of the reaction. So some larger aspects that we see we obtain from this collision theory, and it is based on this collision theory is based on the kinetic theory of gases, kinetic theory of gases, and according to this theory, collision theory of chemical reactions, the reactant molecules are assumed to be hard spheres. So what we assume, the reactant molecules are hard spheres. This is one thing that is also a drawback of the collision theory, because reacting molecules are not hard spheres. They may have bonds, and these bonds actually these bonds oscillates uh, at all the temperatures. So one may not assume, if you are assuming these molecules as hard spheres, then this is a very good assumption. But if we assuming this, we get certain information. So one assumes, according to this theory, reactant molecules as hard spheres, and reaction is postulated to occur when molecules collide with each other. And when these hard spheres are, which are of different shapes, different types, because they are of different molecules, when they collide with each other, the reaction happens. And this is what we see in the collision theory. And the number of collisions per second per unit volume of a reaction mixture is known as collision frequency. So if you suppose if you are performing a reaction into a vessel, so per unit volume, maybe you can consider, or cc means per cubic centimeter volume. So per second, the number of collision will be called that happens between different molecules, the hard sphere, different types of molecules. We call the collision frequency, and that collision frequency we represent with J. This capital J. And another factor which affects the rate of chemical reaction is the activation energy, and that we have seen in the Arrhenius equation. So these two factors actually, according to collision theory, affect the rate of a reaction. One is the collision frequency, and another is the activation energy. So for a bimolecular elementary reaction, it is represented as this: A plus B gives product. The rate of a reaction can be expressed as rate is equal to ZAB e to the power minus A by RT. So rate is equal to ZAB e to the power minus A by RT. These are the two factors. One is this and another is this. R and T, the temperature is there at a given temperature. If the temperature is fixed, so this constant R is constant. So rate depends on this and these two values. So here ZAB is the collision frequency of reactants A and B. So two reactants A and B are there. So this is the collision frequency of these two reactants. Means the number of collisions that happens between A and B per unit volume per second is what Z is. And e to the power minus A by RT represents the fraction of molecules with energies equal or greater than EA, or where EA is the activation energy that we know, and this fraction of molecule which is having energy equal or greater than EA. This is what we have seen in the Arrhenius equation as well. Comparing this equation with the Arrhenius equation, we can say that A in the Arrhenius equation, the pre-exponential factor or the Arrhenius factor, is related to the collision frequency ZAB. So A is actually the ZAB, and rate that there we have seen is rate constant. So rate is how we see ZAB. So rate constant is increased, the rate has also increased. So A is what ZAB means, the collision frequency. And this equation predicts the value of rate constant fairly accurately for a reaction that involves atomic species of simple molecules. So this equation means this equation rate is equal to ZAB into A to the power minus A by RT. It predicts the value of rate constant fairly, accurately for a reaction that involves atomic species, means if the reactions are atoms or the simple molecules, means the smaller molecules. But for the complex molecules, significant deviations are observed. So the complex molecules we see a significant deviations, and the reason this is could be that the collision do not lead to formation of the product. So even with the collision with very high energy, it may not lead to the formation of product because the orientation of reactants may also matter. And the complex reactions, the reactants, if you know that nucleophilic center, electrophilic center, these kind of chemical reactions. So if the nucleophilic center is there in a molecule and nucleophile reaction means attack has to happen. And if the nucleophile, though with the very high energy, but it comes to some other direction and it doesn't collide to the nucleophilic center, the reaction will not happen. It means the orientation does matter. So the collision in which molecules collide with sufficient kinetic energy, and so the term of the effective collision comes. So not only the collision that actually determines the rate of the reaction, but effective collision determines the rate of reaction. And that what how the effective collision is defined? That the collision in which molecules collide with sufficient kinetic energy. And that kinetic energy called threshold energy, which is equal to activation energy plus energy possessed by reactant molecules. And this threshold value I have said in here means what is threshold value? Means from here, this is the reacting energy of reactant molecule plus activation energy. This, if this from value energy value, this from here is called the threshold value, and this include activation energy plus energy of the reactant molecule. So that if the mm, mm, molecules of the reactants collide with the sufficient kinetic energy, and this kinetic energy called the threshold energy, and a proper orientation, and the orientation should also be proper so as to facilitate breaking of the bonds. And that is how if the orientation and the sufficient energy it happens so that it facilitates the breaking of the certain bond, which has to happen for a chemical reaction to happen between reacting species, and formation of new bonds to form products, and also it facilitates the formation of new bonds in the products are called effective collisions. So a term of effective collision comes, and this effective collision includes the certain kinetic energy which is equals or more than the threshold energy, and threshold energy means activation energy plus the normal energy of the reacting species plus a proper orientation which facilitates the breaking of the bond and also the formation of new bonds to form the product. Then such collisions are called effective collisions. And since among all the collisions, very few collisions are the effective collisions. So there another terms comes the probability factor, and that is being introduced later on. So for example, formation of methanol from bromoethane depends upon the orientation of reactant molecules. So this is a methyl bromide, and this is hydroxyl anion. The hydroxyl anion, if you want the formation of methanol from these two reactants, so what we see, this is the methyl bromide and this OH minus is there. So there could be two orientations that one can consider as an example. So improper orientation would be what? The OH minus is towards this side. And if OH minus is towards the bromine, so OH minus will collide to bromine. And this is a complex molecule, so it will collide to bromine, so it will not break any bonds. And what we see, the nucleophilic center is on the carbon and at this point at this end. So, and if it collides with whatever energy along this orientation, it will not lead to the product, and that is why it's called improper orientation. But when this OH minus comes from the back side and is opposite to this bromide, and so the nucleophilic center here, there is a nucleophile, and then in this direction, when the collision happens with a certain threshold value, then it will convert into the product. So it will actually, this collision will facilitate the breaking of this CBr bond and the formation of new OC bonds, and so the product will be formed, and this thing will be broken. And that is how we see the about the about the effective collision. So what we see, the proper orientation of reactant molecules lead to bond formation. The proper orientation is important. That is what proper orientation. It lead to bond formation, where an improper orientation makes them simply bounce back and no products are formed. So even with very high energy, if it collides, it will bounce back. What if it collides in certain orientation, proper orientation? It will, even with the slightly lower energy, it will form the bond, and so this bond will be broken, and so the product will be formed. To account for effective collisions, another factor P, which is called the probability or the steric factor, is introduced. So another factor to account for the effective collision means very a small fraction of total collision is the effective collision. This term P is introduced, and it takes into account this term the fact that in collisions molecules must be properly oriented. And the collisions molecule must be properly oriented. So that the equation that we have seen earlier, rate is equal to ZAB into e to the power minus A by RT becomes equal to rate is equal to P ZAB into e to the power minus A by RT, and P here actually takes into account the probability or the aesthetic factor in the proper orientation of the molecules, and so we get this rate is equal to PZAB into e to the power minus A by RT. Thus, in collision theory, activation energy and proper orientation of the molecules together determines the criteria for an effective collision and hence the rate of chemical reaction. So, in the collision theory, what we see, not only the activation energy, but proper orientation is also important for a reaction to happen, and this was not there in the Arrhenius equation. So, even if the molecule has activation energy, certain energy which is equals to or larger than the activation energy, means the overall energy is more than the threshold energy, means the molecule had already certain energy, and because of the collision, it also acquires certain energy, more kinetic energy, even though it may not get converted into the product if the orientation is not proper. And so, in the collision theory, what we see, the proper orientation and the activation energy means the molecules when they collide after the collision, their energy should also be higher than the threshold energy. Means the activation energy value of activation energy must also be obtained because of the collision. Then only the reaction will happen. So these are two criteria. So collision theory has certain drawbacks as well, as it considers, as I said, atoms and molecules to be hard spheres, which are actually fundamentally wrong because they are not hard spheres, and ignores their structural aspect because if they have a structural aspect, they are bonds, and these bonds always oscillate, they are stretching, and with different type of oscillation, rotation, and this kind of things happens. So this aspect this theory doesn't take into account. So it has certain drawback, but it explains also some important properties about the chemical reactions. So it is important for us. Now here this chapter is also over, and I'll stop, and we'll start from the next class and in chapter, and that will be on the surface chemistry.